Okay, the next presenter is Gary Demos, who's going to present some new work he's been doing on interactive decoding enabled using a file and folder layered compressed structure. Assuming the demo or Demos gods are good, we'll also be having a demonstration. So Gary is recipient of the 2005 Gordon E. Sawyer Oscar for Lifetime Technical Achievement from the Academy of Motion Picture Arts and Sciences. He's pioneered in the development of computer-generated images for use in motion pictures and in digital film scanning and recording. Gary is founder and CEO of Image Essence, which is developing wide dynamic range codec technology based on a combination of wavelets, optimal filters, and flow fields. Please join me in welcoming Gary.
Next, okay. In compression, we're used to multiplexes containing a compressed data stream, like MPEG-2 is typically a multiplex. And the problem with a multiplex is that you have to pre-commit to what's in the multiplex and what's not in the multiplex, which means that if you want to have a layered structure, it's not really very suitable. All you can do is not look at some part of the multiplex, but all the bits have to be there up to whatever layer you want. So this paper talks about using a standard computer directory structure, which works on a regular seek-arm kind of rotary disk. But nowadays with FlashRAM, SATA, and USB, it's possible, there's no seek penalty really, to random access in a file folder structure rapidly enough for real time. So here's the folder structure, exercise for the reader, the quiz is later. What it's really showing is that you can have a really large number of layers there, all the way up to bit exact layers. And within each folder is one file per frame. So that gives you a chance to basically go anywhere to any frame, to any number of layers, up to wherever you want, including layers all the way up to bit exact. So the layers extend from a small image up to, and in the middle ranges, very high compression ratios, all the way up with SNR layers to bit exact. So this is a little bit of a complexity about the layering structure, but basically the point here is that this is a 3/2, 2/3 kind of situation, like 1080p and 720p together in the layered structure. So there's nothing in this layered structure that says that you need a specific factor 2 relationship the way JPEG 2000 does, for example. Most wavelets have specific locking ratios, and what I tried to do was to unlock and be phase neutral and precise. And all the filters are processing to 100th of a pixel accuracy, so there's very fine control. This is also an extension using flow fields so that a wavelet structure can be extended to have the benefit of frame similarity. Although the interactive coding, you kind of have to decode a group if you want to do that kind of structure. And what I'm showing here is intra-coded, meaning no flow fields between frames, although flow fields are used in the determination of the intracode. So this is the more interesting new part. I've actually never talked about this publicly before, although I've been involved with it under the hood for quite a while. The codec, because it's floating point based, is capable of handling high dynamic range and capable of directly coding the new IIF ACEs. I say new, it's been under development for 7 years now, but you know, it's a technically rich project with a lot of excellent work, and there are people here who've been contributing a great deal to it. So when I decode, most of what I'm going to show you here is decoding ACEs directly. Now, I can also take camera raw if I know the input device transform matrix and turn that into ACEs in that first matrix step. Once I'm in ACEs, I'm going to, when I show the interactive demo, I'm going to be modifying values directly in ACEs. So I'm going to be scaling, color balancing, doing all sorts of things directly in ACEs. And then from there, there are several paths out, but the most interesting path is through the reference rendering transform and the output device transform. Currently, the effort has been concentrating on P3 gamma 2.6, P3 gamma 2.6 with high dynamic range using the Dolby monitor, X prime, Y prime, Z prime gamma 2.6, which is a D-cinema, and Rec 709, although we've had trouble having a consistent, clear definition of that for as long as it's been in existence. I got some laughter. I knew my humor was going to work someday. So you can see the potentially very high compression ratios possible from this, even with intracoding. So, and you know, another big gain. So this and because they're layers up to bit exact, I don't have to be apologetic, even though I think the quality is pretty good at compression. Compression is always one of those things, well, how did you decide if it was good enough with this structure and this bit rate? Well, I can defer that to other people. I'll say, well, if you have the bits, you can go all the way up to bit exact. So. And I've been testing this over a wide variety of data types, including 3 to 6 micron infrared, 16-bit, 14-bit, and very high resolutions. Did a test with a Hasselblad H3D in still mode at 7.2K by 5.4K. And I'll be showing you some of the Canon 5D, which is 5.5K by 3.5K. So a lot of range. The interactivity structures, I'm using various different things on the Mac OS and Linux. The OpenGL user toolkit called GLUT, G-L-U-T, turns out to be a pretty good way to go. And I'm showing you today through the Quadro 5000, although I also support the DVS Atomics. And the Quadro 5000 runs under X11 on Linux, so I'm using the X11 interactive toolkit. So here's all the controls I have. Start, stop, exposure adjust, sharpness change, and I'll demonstrate these. So most existing codecs, like MPEG-2, have the quality set at encode time. So if you got a 420 coding in your data set, you're not going to get 444 back out of that. It was set at encode time to be 420, that's what you get. So this basically says that somebody upstream, usually not somebody I've ever met, has decided what quality I'm allowed to have. Now, if I encode it myself, I can set the bit rate. But again, I'm making the decision, and I may change my mind. So having a layered system gives you a chance to match the decoding quality at decode time. So I can defer the decision about quality level. And so if I have a bigger screen or a higher dynamic range, I know I need more layers. If I have a small screen, I don't need them. This is and it's also a way to match the performance of the display device. So let's see if this works. And the Sony guy says he's willing to crank this brightness of this projector up, but we'll see. Okay, so is it running? It's running. Okay, so this is from the Canon 5D Mark II. I'm going to actually sit down while I do this. This was shot time-lapse, so it's a scene. I'll just go back and start with this one. I'm going to put it in a loop here. This is a scene that we shot time-lapse in front of the Griffith Observatory. So we have layers here. We can go down in layers. And we can this is filling the height of a 1080 here. So the next layer up is filling the height of a 2160. If I go back down, you see it's not filling the full width because the Canon 5D Mark II is a 1.5 to 1 aspect ratio. But we fill this screen here, and we can go all the way up to the full resolution. So this is 5.5K by, and we can pan around on the picture, 5.5K by 3.7K. It's a little more sluggish because I'm using more compute power, but, let's work at this one for a minute. And I'll go over here. And then we also have a zooming capability, so we can go in here and have a look at these people. So I'm decoding at the same resolution, but I'm after the fact, after the decode, I'm zooming around on the picture here. Okay, so let's go to the next portion of the scene. So this scene was intentionally shot by Bob Primes for me to be particularly stressful. We're looking in haze at the sun. So I'll put this in an interesting loop here. And why don't I just pick a spot here? So who's that guy? Okay, so here's looking into the shadows. Because we've coded high dynamic range, we have that end of things, and looking at the highlights up into seeing the disk of the sun up there. So, and also when we bring up the brightness, notice that the colors don't become unnatural the way they would if we were doing something unusual in the processing. Because the reference rendering transform is happening after the modifications to ACES, these ACES adjustments are happening in linear light in the same scene space that the camera made. So essentially it's as if I'm opening the shutter or closing the shutter. And the S-curve of the reference rendering transform and the output device transform are deferred to after that. Okay, so we'll go on here to some further scenes here. And I can jump around and go back and forth. It's all interactive. Now these people are kind of interesting, and let's brighten them up and let's do a little spying on them here. So let's see what they're up to. I'm not quite sure, but no good, I'm sure. Okay, so here we get to some night scenes. I have no idea where this is, but maybe you can take a guess. And I'm going to put this in a loop. So if I brighten it up, we'll see that there's, I'll actually just slow it down here so you can see it a little more easily. Actually, if I go up to a higher resolution, that will help slow it down. So we can have a look at the street here. This is with the sun going down. And you see there's really very little noise here. We'll reset the brightness again. And we can go the other way. I'll leave it still here, and we can see that the lights extend fairly far up. So we have a good, strong range here. Okay, this scene's particularly interesting because I'll just put it in a loop. Because the black marble, this is the sun's gone down. It's completely dark out. The lights are the lights on the street here. The black marble, which you can actually see if you go outside. What did I just do? I think I just messed myself up here. So, one moment. The magenta is a palette cleanser for all those who participate in color science. Okay, so we'll get back. So it's being interactive, I can jump right back there. So, all right, so I'm putting it in a loop. And since we're looking, and we lighten this up, we're looking at the black marble out on Hollywood Boulevard here at night. And you can see the noise floor is way the heck down. And going the other way, we can see the lights inside the room there. Now, what I haven't done here is color balance. So this scene's a little yellow. I just ran it all through at 6500. So I can, let's add some blue to the scene. It's looking a little magenta, a little bit of green. So now we've balanced that out. And if I back up to some of these other scenes, like here, we can do the same thing. Put a little blue in that. And let's pick a different scene here. So something else we can do is adjust the contrast. So this is lower contrast, higher contrast. We can drop the blacks, raise them up, you know, all those kinds of adjustment things. And let's do a little bit of looking into the scene here. So, you know, all kinds of interesting stuff to look at here. Okay, so now this scene has some interesting stuff. This kid walks by with this toy, which has been a great test of color range. So this has been kind of fun. So we can see how well are we holding up on the colors in the toy. So let's go outside here and have a look around. We'll go down to the beach. Sorry? What lens? We used 3 different lenses. We used a wide-angle zoom, a medium focus zoom, and a telephoto zoom. So, you know, depending on which shot, you can kind of guess from the shots which are long shots. And some detail under this guy. Okay, so I'm going to switch scenes here. So this is from Bob Prime's single chip camera evaluation. Some of you here worked on this. This is the Alexa version of the scene. I'm going to get the F-35 version of it here shortly. So this was a low light scene. The Bird Motel is a good test on the high end. See how well we're doing up there. And on the low end, we got a guy sitting in Bob's Porsche here. And then we have this nice scene. The challenge on this is looking out the window. So he called it overexposed. So he wants to, and this one he called underexposed because there she is standing in the shadows. Okay, so let's go in and have a look around this scene. So this being an Alexa, that's the 1920 1080 layer. There's a layer of half that, and half that, and half that. The next layer up is the 2880 by 1620 layer. So we can go over and have a look around in here. And there are layers up to bit exact here. So we're going in pretty far on this. So I can put in a little loop. And I'm just going to climb the SNR layers. You're probably not seeing much difference, but at some point she'll get quite slow. So right there. So what this is doing is there are 2 SNR final layers. This one is the noise-reduced original, and then the next one after it is the bit exact original. So the noise-reduced original gives you more compression, and in some ways is a true representation of the scene. But it integrates the bit exact residual as if you might think of it as a recourse to knowing what was really there. So, okay. And the noise definitely comes back when you do that stuff. All right, so here's my palette cleanser. Now this is from the D21. This is Joseph Goldstone here from ARRI, who also has worked on the IF stuff. And the D21 shot from the camera assessment series. Now this is a 4:3 aspect ratio, a little taller, and gives us, how am I doing? Good. Gives us a chance to crop on the fly when we decode. And going up here, we have the full resolution. And again, we have the resolution all the way up to bit exact. So, but it'll get slow. So we get to the spot. So the next image that pops up, that one, is all noisy because the noise reduced original and then the bit exact. So something I didn't show you yet is adjustment of saturation. So we can, let's go down a little bit, resolution. So there it gets too colorful, and there it gets not enough color. So we'll reset that. Now, the big debate with Joseph, of course, is whether the white directional ball is brighter or his head is balder. He's, of course, a good sport about this. I don't know if he did that intentionally, but notice this is a backlit color chart. I don't know if they even thought of the idea of putting the light of the color chart on the front side, or maybe they have a reflection card, I don't know. Okay, so what I'm going to show you here, I'll show this twice. This is from the Viper from the camera assessment series. And this is playing with a quadruple process decode. You can see it's dropping about a couple of frames a second. So it's almost real time, but not quite. So in software at HD 1920 1080 with a little bit beefier machine. This is a 6-core, so a 2-chip 6-core, 12-core is more than real time. It actually will do quite a bit more. Now, the reference rendering transform output device transform is happening in a 3D lookup, and that's being done in OpenGL on the GPU on the way out. So the pixels are actually going up as half floats, OpenExr half floats after the decode and the reference rendering processing. And then they go out to the GPU and get turned into the 12-bit dual link output. Now, we're getting this signal decoded here back to the projector back there, so there are actually some losses in that part of the path, but the decoder is actually putting out 12-bit dual link. So this is kind of neat because we got some nice bright highlights from the camera assessment series. So that's how hot that one is. We got the out the window there. And this is how fast it is on a single process. It's multi-threaded, but not multi-process. So we have the detail out the window, and we also have shadows. These scenes were all intentionally shot to be tough, like Bob Primes did with the single-chip camera evaluation. So I think that's it.
Have any concluding comments?
No?
Okay.
We can take questions or
okay.
whatever.
Questions for Gary? Just while you get to the microphones, I just wanted to mention a few phrases that I heard. Technically rich environment and processing complexity. Would you care to comment on how technically rich and how much processing complexity we're talking about with this kind of system?
Oh, I have no idea what I was saying. Did I actually say those things? So this is a 6-core, and I would say about 20% of the computing with the RRT, ODT, 3D lookup that's going on in the GPU and OpenCL. And Thomas True of NVIDIA helped get that working so that it would go out the dual link. It was using about half the processing power because I multi-threaded about half the computes. So you saw it almost hitting real time when I send up 4 processes. I could actually make interactive with 4 processes, but then I got to code all the interactions between the processes. And I'm always looking for the more powerful machine so I don't have to code.
Right. Any other questions? Is there a question at the back? Please go to the mic.
Hi, that was fantastic. My question is actually a simple one, and if you are using, if you're not using GPU, but you're using CPU, and you're applying a compander effect on the basis of the coding, that same coding, could you in essence net the exact same result?
I have no idea what you just said.
Oh. I'll take it offline with you later.
Okay.
But the other follow-up to that is if you are relating, if you're opening up in the a particular exposure range, and you're exploring now bringing things into and out of that range. The control parameters that you have there are, that affects all the layers at once, or can you affect one layer versus another layer?
The interactive controls that select between layers put you on a given layer. Once you're on that layer, then the interactive controls let you adjust what you're seeing. So I could have been doing all those adjustments on the little tiny picture, including the zoom up and all that sort of thing. I guess there's a natural, where did I pick off the layers, and that's basically a decision made early on. That tells you what resolution of aces you're going to decode. And then once you have that resolution, then all the rest of the processing is, to taste, if you will. Although, if you set everything at, I kept restoring back. There's an R key there that says no matter how much I made everything look terrible, I can restore and reset. So I use that a lot because I move it around to look in the shadows, but then I don't want to see them lifted up like that.
Thank you, Gary. Next question.
Hi, Mike Bergeron. I'm just curious, from the original uncompressed files that you start with, once you get them into your platform, it seems like they must be much bigger. How much? Or are you actually getting a compression gain here?
So I'm starting with OpenExr ACES, which I use the PIS compressor, which is about, I don't know, 1.7 to 1 or something. I code it through my layers. It showed on the one slide, so you can look at it if you want later. But the noise-reduced original to bit exact, or close to it, is because it's a modified thing. It's not the original. That's usually about 4 to 1. And then the bit exact comes out about the same as the PIS or zip or whatever. It's 1.7 to 1. It depends on the noise level, because that last layer or two is really putting the noise back in to give you the bit exact. I'm trying to preserve all the details and the information of the scene in the higher compressed, 20 to 1, 40 to 1, 100 to 1. And of course, if you're going for a lower resolution, you have a lower bit rate from every notch you go down.
But the aggregate, how does that compare to the original?
The aggregate,
file?
as I said, is about the same as the PIS or zip, or it's
okay.
If you use the built-in PIS OpenExr compressor, which is bit exact, it'll give you about 1.7 to 1. So if you add up all my layers, you'll get about the same, maybe a little more, 1.9.
All right, thank you.
Might beat it a little bit.
Thank you. I think we have time for one more question. Any further questions? No? Well then, please join me in thanking Gary.